are in a Opero company, and I would like to invite you to know our journey, very trip all the way, and how we reinvented our cloud architecture using BGP protocol for OpenStack running from OVN. So, who we are, Opero. So we are a European private technology company founded in 2015, and we are providing dedicated cloud computing services for demanded markets like the European space sector. So we are specialized in storing and processing big assets. Those data were pretty synthetic. I would like to present it in a more graphic way. So you can imagine above our heads there are a bunch of satellites. Part of them represents our business partners that are constantly taking us in our Earth and sending back to the Earth to our ground stations. And here comes Opero. We and our partners are collecting this data. We are packaging it, store it, and on demand we are fetching this data, process it, and present it to our customers in some nice way. And of course, with every new iteration of the satellites, it's a big improvement of the technology, bigger data to receive, bigger data to store, and much more things to compute. And yes, we are doing it on open source services. We have about 10 regions, both for public and private clouds, and we have huge storage where all this data is located. So what we're gonna talk about today? Why L3DC? So a year ago, I had the opportunity to present on the summit lecture about having OVN at scale and about our struggle with layer 2 networking. So yeah, we had a challenge and how to make this layer 2 big network domain scalable and big enough to fit our needs. So we struggle. We had our problems that we decided to finally solve in a step that will be our future. Then this solution, we knew it won't be only for our cloud, because we're gonna change our infrastructure both on the cloud and also on the network part. So we sit together and trying to find out how to fix this problem, how to make the scalable network. You can ask what kind of problems we have with the layer 2 network, why we do change. So I asked the networking guys from their perspective what are the issues. So we tried several approaches. Both of the approaches were fit to do kind of HA, traffic balancing, and redundancy. We tried with some kind of MLAC implementation. We tried EVPN solution. Both of the solutions had problems. There were proprietary solutions made by vendor. All the solution has some issues, but there is this issue where in some dark places that we couldn't easily debug. They were not so verbose that we can easily go through the problems and find out what's going on. And like I said, those solutions were. Sorry? Oh, no. I thought I disabled this power semester. So those solutions were made by vendor. Even if they say that they're implementing some RFC-based documentation things, they are only for a specific device producer. So there is kind of vendor lock, and we cannot mix the devices together. From team perspective, L2 network issue, well, we have to manage and administrate big layer 2 networks. So it's challenging itself. Then we have OVN. which has its legs on starting from layer 2 to layer up to, I don't know right now which one, and it's using the same space as our network devices, which means anything that's happening on the network device may affect your OVN, which means it may affect your neutron service. If it's neutron impacted, your whole service, all the cloud service is impacted. And the contrary, when you have problems somewhere between open flows on your OVN, it may affect your network device. That said, it's hard to define where is the root cause of your problem, because it can be either on your OVN or it can be on your network side. Sorry, I don't know what's going on. I will press shift, that's why. So there was an example, but one of the examples that we were struggling to recently, but I guess we are short in time. So, like I said, we sit together and try to find out where we should go to provide a scalable network. And of course, we know BGP is working for pretty big scale. There is internet driven by this protocol. So, why not build on that? This approach is not really new in OpenStack. It's existing some time. The idea of limiting layer 2 for the sake of the layer 3, but it's mostly for our dynamic public networks. So for our floating IPs and other IPs that are constantly changing its location within the infrastructure. And yes, it's on OpenStack, for example, in OVN BGP agent, other agent that we heard about today, and I just recently discovered that we have it also in our OVN since version 25.3, I guess, which is actually mind-blowing. But yes, there are some possibilities still right now on OpenStack. But we wanted to go full in. So, of course, we wanted to do it like layer 3 networking for our public networks, but also we wanted to put on a layer 3 network our internal networks, so the networks which every services in OpenStack is connecting, our storage network, SEF and other storage systems, also on layer 3, and our network like API services. For the sake of the, just in case, we wanted to keep our simple out-of-the-band layer 2 network just for management of the process. So we wanted to go from this, which is more or less representation of what is on native OpenStack deployment, to this. So the comparison is pretty visible. What is really worth to mention here is the layer 2 network domain. So all your hosts and your switches and your routers that are sharing all this large spread network, and this is the internet connection. What is important in our approach? For us, right now, for implementation, every host, it's L3, the accessibility to it, it's almost the same like any service in the internet. So, how does it work? We check our infrastructure, and for the configuration we found out we have a profile of servers, how we wanted to connect it. So we defined a group of servers that are configured in a specific way. For example, we have control planes that are doing our network components like neutron and OVN, which are only needed to be connected to our internal network. We have our network nodes that are doing SNAP gateways, and of course control plane nodes where the rest of the OpenStack is happening and API endpoint existing, and hypervisor so compute. What we did for a control plane as a static configuration, because those hosts are specific, there is not much dynamic in it. So these hosts are connected to our network spine leaf architecture. So we have two leaves. that we can connect to on this node. We have one PCI device with 2 ports, and those 2 ports, they give us VLAN interfaces that are doing the BGP session uplinks to our layer 3 correspondence services on leaves. This part is located in a VRF, internal VRF, which is under the control of our BGP service, which is FRR. That means that all the configuration here is fetched by FRR and configured in a way it's see that we have a placeholder for IP, which is a dummy interface internal with a static IP, and this IP is announced to the rest of the architecture. And from the other perspective, we receive prefixes, roots, that define our default gateway as an ECMP routing, so we are benefiting in the traffic balancing and redundancy for this case. We decided to have a VRF root leak, which means that we are taking roots announced in this internal VRF to the master default VRF, just to have the benefit of L3 in the for every application that is running on this node and the default connectivity. And like I said, we still keep this simple layer 2 networking. It's also included in its own VRF. Network node is slightly different because this node is the place where dynamic IP is coming. So internal VRF is almost the same, but please notice we have here 2 network devices. 2 network devices which are here, also with 2 ports. To get this opportunity to go with the traffic with full the power of the compute, we are placing these VLAN interfaces for these interfaces to the internal VRF. Rest is the same. And to the external VRF, when the dynamic matching is happening. Here, on this placeholder dummy interface, we don't have static IP defined, because this is an interface which is controlled by an agent that is doing this dynamic part. And for the OpenStack-based OVN connectivity, we have here the bridge from the provider network. I know it may be slightly less visible here, it's more complicated, but the concept is multiple. We have this internal VRF here, we have external VRF, idea is the same, and any other internal or external network that we would like to provide to our compute, to our VMs, because this is a compute node. And one of the differences here is that still we have 2 PCI devices with 2 ports, but this time we decided to put port A from first device to the VRF and port B from the another PCI device to the VRF, and the second port we desired to do storage traffic. So it's a matter how you would like to balance your performance and your capacity of a network transfer, depending on your demands. We found it most suitable. So, to sum up, we have our layer 2 network for bootstrapping host, classic way, DXC, DHCP, and so on. We have this network also in VRF for the sake of the architectural convenience. We have a marriage with challenges for configuring this whole network stuff on your host. We are using systemd network, DNet plan, and FRR on the same host, which, like you see, it's pretty big. There's like for the compute right now for this number of networks we have 49 computers with configuration files with more than 100 lines of the code. Every isolated network that we would like to connect to the infrastructure is in own VRF. And for simplicity, we decided to use unnumbered BGP for our uplinks that is doing BGP sessions. So we are using IPv6 link local versus set up BGP session, which helps us a lot because imagine if not, we then need to set up IP on each of these interfaces for whole infrastructure. It will be huge. So this helps a lot. And like I said, we are using Afera to control the things that are happening in a specific VRFs. And we have via IPs and unicast IPs controlled by TLIve, but we have to remember that this TLIve has to support VRF configuration and L3 layer checking curve, because otherwise there is no L2. So I believe that the one from current Ubuntu is working fine, 2.8. So about OVN BGP agent, we heard something about it in the previous sessions. So this is an agent that is doing this dynamic configuration according to what is happening on OVN. So it's setting your floating IPs on compute. It has several modes, so a few drivers that you can connect these agents both to northbound the database of OVN or southbound. We prefer this northbound because the database is usually smaller and it's less even busy system. And it has several ways of exposing, so configuring your dynamic IPs. One of them is Android, which is exactly using IP root stuff to configure. Another one is using another OVN to do this layer 3 networking. And third option is more related to AVP and stuff, so which are not for us right now. So, like I said, it's what OVN BGP agent is doing. So it's waiting for the event on OVN. When something happening, it configure IP on your network interface. It set up IP rules, your neighbor stuff for your small L2 but still stuff, and some flows on OVNs. And of course clean up the things when the configuration is not needed in the moment. And there is some process that is constantly checking if OVN configuration is synchronized with what you have in a configuration on your host. And if you would like to have the details, you can go for a walk to Luis and check it, or we can talk after. I won't go for the details how the packet is flowing. This is a snippet for the picture of how it's going on the desktop. So there are things. Okay, and like I said, we have many VRFs we have VRF for every isolated network that we would like to provide to our customers. Currently, OVN, from my knowledge, is that it supports only one. So, because we wanted to separate these networks on the VRFs on the host, not on the network, we decided to do a slight changes to make add new feature to the OVN BGP agent to provide configuration for any VRF that we would like to attach to some physical network. In the same way how it's working for a default one. So in this case, in the configuration, we added options that you can define another FizzNet, whatever it is, physical network, and override configuration from the default one to the specific one that you are in need. So for example, our Octavia management network is also done. So, what do we like in this approach? From network perspective, this is BGP. We know it should work. We know it scale because we have a proof we see internet how it's working. And every device that pretends to be called a router should do it. And we limited layer 2 network there. And what is important for the team, they like became our peer operator. So they are delivering a peering service for any other services that are based on this network. From cloud perspective, well, OpenStack is just working, it needs IP, so it's fine. What is important to know that right now the approach for it is every service, every host that's appearing on our infrastructure, it's IP. It's available just like any other IP on the internet. So it's pretty easy to define where the boundaries are, because we know where is the part for network and where is the part for cloud. Still, we can deliver a layer to network. They are encapsulated in the GX1 engine, but there is no VLAN network, because we don't have VLAN for our customers and so on. Okay, so we implemented it. We have already 2 infrastructures that are working in this architecture, and we are gaining experience. And we are starting to discover, is it the best solution that we can have? Well, configuration for network, it's getting bigger and bigger with every network, every VRF we would like to provide. Because for every VRF we have to configure VLANs for the uplinks, we have to set up BGP sessions and so on. Even if it's layer 3 with the BGP, we also struggle a bit with our vendor implementation on our devices. There are some functions that are working not exactly like they're supposed to, or they're not working, or they are crashing our device when we apply services. It happens still, but it's iterative. And of course, this is no new thing. We have to learn how does it work. From our cloud team perspective, it's corresponding to what's happening on network team. So the configuration, yeah, we have to do it anyway. We have to be also careful about the process of delivering our tests. They are appearing in the system in L2 network, so we have to be sure what's the process of changing this layer to connection to the L3 to not disconnect our host from infrastructure. And if everything is working fine, it's fine. But things happening, so then you have to be careful. And yes, before that, of course, we had our OVN experience. And right now, well, we additionally to that, about the networking knowledge scope, we have added new skills. Well, every host right now is a router, so we need to know how does it work on the cloud suite. And the thing is also that, yes, this is a new thing. We also have our legacy things, so old L2 machinery still somewhere there are regions that are working. We have to keep them maintained and do automation for both L2 and L3. So and if we say there is L3DC, always there is a small piece of L2 that has to happen somewhere. So it's spread, it's distributed on every host, because this packet flow has to be transferred from your OVN to the layer 3 network. So there are some tricks that are happening there to do so, which we have to be aware of. Okay, so this is how we implement that. Here I can present you some of the struggles that we had during our implementation. Like I said, we have on our host like few services that are trying to configure its network stuff. So we have a Zebra service that is trying to configure your devices. Also systemd that's doing the same. And there are some clash together, and there are some problems. The problems are known, but still not really fixed. For example, we have to give up for a while with our fancy BGP number stuff and tell her to not configure a number BGP like it's not existing, and using some tricky way of doing it via IP4. Because simply when we are starting secondary network, it happens that FRR lose its prefixes, for example. But we hope that in the future, either community or we found a root cause of this issue. Actually, I don't know how much time I have. So another thing to mention is not problems, but machinery that it's how it's built online to deliver VRF services. I don't know how you are familiar with VRF onlines. They are not so, in my opinion, they are not so easy to know. Like I've been at many places where there is a just different network stack. Here it's something different. There are parts of layer 2 and layer 3s. In our case, we put, like I said, every interfaces in a VRF, including internal VRF. But our services are working in a default, which means that they have to connect to the network device that is in a VRF. If your application is not aware of existing VRF, it means it cannot be used. You cannot use this socket. So there is a trick to override it. This option tells the system to allow to connect to the socket whatever VRF it's placed. So yeah. And by default, right now on Linux, there is no default configuration that you can connect between VRFs. This is because that your lookup rule in your root table is in a higher priority than your lookup table for L3 and so this table that is looking in the roots for every VRF. Which means that when you are trying to reach interface that is in VRF, it's going through local instead of your L3 and the table. So you have to change the priority of your rule to first look at this VRF table to reach the interface and IP in the VRF. So you have to do changes in IP rule, but then you have to be careful to not allow systemd or other services to change it back, because it may do. Sorry. There is another part of this story. It's similar with your dynamic IP, but it's like contrary. You prefer that your unknown dynamic IP, the traffic to this IP is going to your OVN device, not to your device in your VRF table. So you have to also be careful and set up the priority. This is also our small change in agent to put the rules in a higher priority VRF table. Okay. Actually, I don't know how much time. To have some questions. 5 minutes. Perfect. Okay, and last thing that I would like to talk about is this mechanism to resynchronize OVN agent. It's done some period of time and on every service startup. The problem is that OVN agent is the service with one thread, so it cannot do it in parallel. And this process of synchronization takes time, so it's about 10 hours per second. And yes, every change that's happening during this time of the synchronization is queued in a queue for execution later. But when you have many items to configure, you can wait about 2 minutes for 1,000 ports, waiting until your IP is ready. You can move your customer workloads to timeouts because there will be no network. So, what we can do about it? First, okay, maybe what is happening, why it's so time consuming? Yes, it's configuring all the IP rules. It has to fetch all details for the port from the OVN. It has to remove all this old obsolete configuration. So it's taking time. And we are working on some kind of proof of concept. How we can fix it? Of course, we can think about multi-processing, multi-threading, and so on. But first, we would like to do some more easier approach. We do some code optimization, which will help a lot. But also, we are thinking about changing the way how it's configured. All these dynamic IPs in the host. So, how it is right now? Like I said, you have every IP configured on the host existing in your IP rule and IP rules tables. What we are thinking about is changing this behavior to have a rule, but only for the subnet that is happening on this host. So it's much easier to maintain it if there is fewer entries. So it should do the job. We made some benchmarks, and it's like 10 times faster. But we can go through 1,000 ports in less than 20 seconds, which is fair enough for. And there are some also additional consideration here, but maybe another time. So, thank you very much.